compressor is a dual-action positive displacement reciprocating air pump. As a positive displacement device, it moves air by trapping a fixed volume and mechanically reducing its space, making the delivered flow rate primarily a function of RPM. Its reciprocating motion varies the chamber value and uses check valves to direct air through the system. Dual-action operation compresses air on both piston strokes, doubling the effective flow rate and providing smoother, more continuous delivery with pistons 180 degrees out of phase. The relief valve protects the system by venting air when internal pressure exceeds a safe threshold.
Alright, so for a quick fluid mechanical overview of how it works, we take a look at one of the piston assemblies. We define a control volume bounded by the head of the piston, the walls of the cylinder, and then the actual manifold head. As the piston moves down, this control volume is increased, which creates a pressure difference between the pressure in the cylinder and the pressure in the intake. This forces air from the intake into the cylinder. And then for the discharge stroke, the opposite happens. The piston moves back up, decreases the size of the control volume, which creates a pressure difference again between the pressure in the cylinder and the pressure in the reservoir. This air in the cylinder is then forced up through the outlet valve and into the outlet manifold or reservoir.
Let's take a look at how the piston assembly works through the whole system. If we take a look at the head block manifold, then we can understand that the pressure differential created by the piston's downstroke allows the air to pass from the intake through this reed valve. On the discharge stroke, it goes through this reed valve, through here, and then out the outtake. This side of the system is for the second piston assembly, and they work exactly the same, but 180 degrees out of phase. The Reynolds number is high due to low viscosity and small valve diameters. Thus, sudden expansions and bends create strong adverse pressure gradients. The boundary layer can't stay attached, thus flow separates, forming vertices and recirculation pockets right behind the valve slots, causing inefficiencies in the system. Since the Reynolds number is high, the flow is turbulent.
For the system, we can reasonably model the working fluid as an ideal gas and treat the compression process as quasi-equilibrium. This is because the piston speeds are low relative to the speed of sound, thus allowing pressure and temperature to equalize rapidly throughout the cylinder. This also supports the assumption of spatially uniform pressure, using a constant polytropic exponent to represent the behavior of each compression cycle. Having well-sealed pistons and valves justify neglecting leakage, and because flow velocity through valves and passages remain well below Mach 0.3, density changes in these regions are minimal, allowing incompressible flow relations.
So we drove the pump with a drill, and we measured the RPM with a visual tachometer on that piece of tape. We also measured the speed of the exit velocity with an anemometer. So using the data that we found from driving the pump with the drill, we found the flow rate against RPM. We did this by using the formula, the change in volume of the cylinder, and we multiply that by 2 since there are 2 cylinders, and times the rotations per second. In graphing it, we found the theoretical line versus the actual line from our data. And the actual line from our data separates from the theoretical line at larger RPM because when the pistons are moving faster, air has less time to enter the cylinder before it starts its discharge stroke, thus creating larger inefficiencies. Using the values we obtained, we also calculated power, with a typical efficiency of about 0.8. When the ambient pressure is close to the pressure in the reservoir, the power required to drive the system is about 0.15 kilowatts, while when the reservoir is near the maximum that the pump can withstand, at about 6 bar, the power required to drive the system is 1.7 kilowatts.
From the piston diameter and the 2 piston positions, we get a purely geometric volume ratio of 4.66. However, this is not equal to the pressure ratio because the system is not isothermic. The assumptions Nick just explained allow us to use the polytropic relation to derive the pressure ratio. Since our system has some heat transfer, but not 0 or maximum, we assume a polytropic exponent of 1.2. And that gives us a pressure ratio of 6.33, a much more realistic value that lines up with the 6 bar relief valve pressure.
Thank you for listening.